Hello, teammates. It's your host coming to you from the physics bunker. You're going to be doing this on the 26th of March, 2020. We're going to get back to our workbook for a little bit. We're going to go back to some special problems tomorrow. But our workbook is feeling lonely, and I thought we could get some work done. We're going to do problems 4 and 5 on page 154. I'm going to pause the video now, work on problem 4. Don't spend more than about 8 minutes. And once you've done that, come on back and we'll do the solution. It's good. So my assumption is you've taken a shot. So let's look at Tarzan. He's going to swing from point A to point B. He's going to start at rest. Hopefully you caught that. He's going to start at rest. We want to determine how the tension changes and why from point A to point B and then to point C. So qualitatively, look at this pencil. I got my black Ticonderoga. I can do surgery with this. Look at that. Qualitatively, because he's at rest, and we know that the force centripetal is related to the mass velocity squared over r. The r doesn't change from A to B. What changes though, and his mass doesn't change, what changes though is his velocity. And so as he goes from A to B, the force tension is going to be increasing. Right? Because we know in this case, so his weight doesn't change, but the force tension from A to B is going to increase as his velocity increases. It's good. At point B, he's swinging at 7 meters a second, vine 8 meters long. How hard does he have to hold on? I think a free body diagram is in order. And I know the inward force, the up force here, the force tension is going to be greater because the centripetal force is directed towards that center of rotation. I know his force gravity is 800 newtons, and I want to determine his force tension. We're going to need to calculate our centripetal force. And I've done this in advance to speed this along. If you see any errors, send me a note. 8 meters is going to give us a force centripetal of 490 newtons. So our force tension, our center seeking force, our net force up is going to be 490 plus our weight 800. It's going to give us a force tension of 1290 newtons. I apologize for the table shaking. I need a better plan. At point C, the vine catches on a branch. So now what happens is his center of rotation goes from there to there, and the radius changes now to 2 meters. We have to calculate our force centripetal again. Mass hasn't changed. Velocity hasn't changed. But our radius has changed. We're going to get a new force centripetal, much greater, 1960 newtons. I'm going to knock out a quick free body diagram here. Weight hasn't changed. But now our force tension is 1960 newtons, our force centripetal, plus 800 newtons, which is going to give us 2780. I brought my ruler too. Let's tighten that up. I should have left us more room to do this. I was trying. So just so you know, if I keep these workbooks 100 pages or less, the the binding essentially becomes free. And there's a whole history on why I use this binding so well. So lays flat. It's good. Hot diggity dog. Path he takes. If he slips off at point C, what he's going to be in free fall. So he's not going to. So that what the uninitiated will say, he's just going to continue in a circle like that. But I know the people in the super second hour and the fighting fifth hour, they know that's not going to happen. They know he's going to be in free fall as soon as he lets go of that rope. And you're going to have that nice parabolic motion. Is good. Let's look at this next one. I'm going to include a video when I post this on Schoology of some Air Force pilots in training getting put through an apparatus like this. It's pretty interesting. It's pretty interesting. This is actually a Russian system. It's going to spin around. Got a cat visiting. Go to somewhere else, please, baby. It's going to spin around. And it's going to generate G-force. So it's going to increase. Luna, go. Yes. It's going to generate a G-force in the astronaut. So I'm going to ask you for how many revolutions per minute. Yes, thanks. Go. I'll come pay attention to you later, okay? I'm sorry. Go. So focus on getting how many its velocity, and I'll take you through the revolutions per minute. Get its velocity while I get rid of the cat. Come here. Okay, and I'll walk you through the revolutions per minute. So we want to figure out this. It's very similar to a problem we did with Mr. Thomas Palmer on the video. So that the astronaut sits kind of there like that. So she's going to feel a normal force towards the inside like that. So in that normal force, we can recognize that as a weight. So mg equals our centripetal force, mv squared over r. Masses are going to cancel. G times r equals velocity squared. We're going to square both sides so that the square root of g over r equals our velocity. Go away, honey. So we're going to use 10 meters second for our g radius of 18 meters. And we're going to 10 times 18, 180, square root 180, 13.41 meters per second as it rotates around. And I'm going to pause it there. I'm going to keep this at just about 10 minutes. That's good. That gets us where we want to go. Teammates, have a great day. I'm going to go pay attention to the cat a little bit.